Okay, so we're now in part 2 of this economic example where we've got a consumer who has a certain amount of wealth, which is the money that they have available that they're going to spend on two different goods, and those two goods have different prices, and we want to figure out the quantities that the consumer should purchase of each one that will maximize their utility. And in other words, we're trying to sort of optimize the way that this consumer should spend their money on whatever these two goods happen to be. All right, so we left off the last video with a discussion, or at least leading into the discussion of what the actual constraint should be for this situation. So what I want you guys to do is take a second here and think about, if you haven't already, and try to write down explicitly what the constraint should be for this situation. All right, so the first part of our solution should be to identify that there is actually a constraint at play in this scenario. All right, so we can come up with a constraint equation for this thing, and if you haven't already, written down an explicit formula for this constraint equation, I want you to pause the video and take a few seconds, think about it, and try to write down whatever you think the constraint equation should be. Right? So, what is the thing that's holding this consumer back, or what are the sort of rules that the consumer has to play by? All right. So, take a second, pause the video, see if you can come up with a constraint equation. All right. So, hopefully, you paused it and came up with something here. And the main thing that our consumer has to work with here is the fact that they only have so much wealth, right? They only have so much money to play with. And so the idea here is that our constraint is going to be given by what's called the consumer's budget. In economics, this would be called a budget formula or a budget equation. And the idea is that they want to buy these two goods, and they want to purchase Q1 number of good 1 and Q2 number of good 2, and you know the prices of each P1 and P2. So what this tells you is that to figure out the total cost that the consumer is going to spend on quantity 1 of whatever this first good is, well, that's going to be the price of that good times the quantity purchased. So that's going to be P1 Q1. Right, this is the total cost of good 1. Whatever that first good happens to be. Maybe it's Snickers bars or whatever I said in the last video. And then do the exact same logic for the second good. Right, this is going to be the cost of good 2. And the total cost together, of course, we'll add them. This should add up to whatever the consumer's budget is for these two goods. And that's this amount of wealth, W. All right, so this thing is our constraint equation. All right, a so-called budget equation. And of course, this is not a course on economics, which is why I'm not really, playing up all these concepts, but this is referred to as the consumer's budget equation. All right, so this is their budget that they have to work with, and this is going to be our constraint. So the thing that we are trying to maximize, right, so we want to maximize the consumer's utility, which is given by Q1 to the alpha, Q2 to the 1 minus alpha. And again, this is a very general thing. If I scroll back up here, you can see here that this alpha parameter is just any number between 0 and 1 right now. For the specific consumer that you're looking at, I talked through this a little bit last time. For the specific consumer you're looking at, the different values of alpha would tell you how much they enjoy or how much utility they get from quantity 1 of good 1 versus quantity 2 of good 2. All right, so if you absolutely love Snickers bars, and you maybe don't love Hershey's bars as much, then alpha might be pretty close to 1, which would make your enjoyment from quantity 1 higher than your enjoyment from quantity 2. All right, so, or your utility, I should say, right? It doesn't have to be enjoyment. It could be a variety of things. Utility is a very broad term. Okay, so regardless, the thing that we want to maximize is this utility function, q1 to the alpha, q2 to the 1 minus alpha. All right, so what we have to do here, we've got the thing that we want to maximize. Remember that this, this function would be called our objective function that we're trying to maximize. And we want to maximize our objective function, which is our utility function, subject to the constraint that is our budget equation. All right, so we can set this up as a Lagrange multiplier problem. So Lagrange multiplier setup would look like we want gradient of f. F is a bad thing to call it here. It's not actually f for us. Our objective function is called u, so let me use that language. Gradient of u should be equal to the gradient of g with some scaling factor in front of it called lambda. And we haven't really defined what g is. So let's take a second here. Let me get rid of g, and let's just walk back up here for a second. Right, our function g is actually going to be this piece of our budget equation, our constraint equation, right? Because g is supposed to be the function that's constrained. So g, in this case, would be g of q1, q2 equals w, is one way that we could write our constraint equation. And so, you know, going back down here to our setup for our Lagrange multipliers, I can say that this should be gradient u should be equal to lambda gradient g, and we know what u and g are supposed to be based on you know, u being this utility function, which is in the green box, and g being this budget constraint that's in the yellow circle there. All right, so the last part of our Lagrange multiplier setup is going to be the fact that we still have to satisfy the constraint equation, which specifies that g of q1 and q2 should be equal to whatever the consumer's wealth is, so this value w. So this is what we want to work on, and right now we just want to figure out you know, in a little bit more detail what these gradients actually look like. So to do this, I just want you to remember, let me use a different color here, I want you to remember that the gradient as an object is the derivative with respect to whatever the first variable is in the first component. In this case it's q1, and the derivative with respect to the second component in the second variable in the second component. So that would be the partial derivative with respect to q2 in the second component. So for us, this would look like the derivative of u with respect to q1, derivative of u with respect to q2. And we know what this is going to be. If I go back up here to our objective function, just so it's on the screen there, the derivative with respect to q1, the partial derivative that is, remember that we just treat q2 like a constant when we're differentiating with respect to q1. And so this utility function looks complicated, but it's really just a power rule is how we want to tackle this derivative. So this turns out to be, you know, bring alpha down, q1 to the alpha minus 1, q2 to the 1 minus alpha. All right, and do the same thing for the derivative with respect to q2. Now we're going to bring down the exponent on q2, which is 1 minus alpha. And we're going to have q1 to the alpha, q2 to the 1 minus alpha minus 1, so that's going to be minus alpha. Okay, so those are our derivatives with respect to q1 and q2 of the utility function. Now we want to do the same thing for the gradient of g, which again is our budget function, right? This is the thing that tells us, price 1 times quantity 1 plus price 2 times quantity 2. And so if we're differentiating this, again, remember we're taking derivatives with respect to q1 and q2. So, looking back up here, the derivative of p1, q1 with respect to q1, well, that's just going to be p1. All right, so this derivative is actually a little bit easier, a little bit more straightforward than the last one. And of course, if I were to differentiate p2, q2 with respect to q1, all of that is treated like a constant with respect to q1, so that's all just going to vanish, right? This will all vanish when I differentiate with respect to q1. And then, of course, if I differentiate with respect to q2, the opposite would happen, right? The first term would disappear, and the second term would turn into just p2. So I'll put that down here, all right? So the gradient of our budget equation is p1, p2, a very straightforward derivative. All right, so putting this all together, right, now that we have exact formulas here and here, let's go ahead and put this together into a cohesive system of equations on the next page. All right, so our Lagrange multiplier system, now that we've got a little bit more information under our belts, this really looks like alpha q1 to the alpha minus 1, q2 to the 1 minus alpha should be equal to lambda p1. Right, that's our first equation from the gradients, the gradient portion of the Lagrange multiplier setup. And then our second part is going to be 1 minus alpha q1 to the alpha q2 to the minus alpha should be equal to lambda p2. And lastly, the last line of our Lagrange multiplier setup is always going to be the constraint or possibly constraints. We won't do the multiple constraint situation in this class, but you can absolutely figure out optimal values when you're considering more than one constraint at a time. And this is really a more realistic way to go about it, because very often there's more than one thing holding you back in any given realistic situation. But regardless, we'll put our constraint equation at the end here, which is p1 q1 plus p2 q2 equals whatever this consumer's wealth W is. All right, so this is our Lagrange multiplier setup. And now the fun part, we need to figure out how to go ahead and solve this thing. All right, so what I want you to do right now is pause the video, take, 5 to 10 minutes, go ahead and really work on this. All right, I want you to try and figure out just what the heck you are supposed to do with a system of equations that looks like this. Especially since it looks like it has about 100 unknowns in it, right? It looks like a complete jumble of unknown values. So I really want you to remember what you're looking for here, right? The things that you really want. The things that you want out of this analysis are Q1 and Q2 coordinates. Right, this is what you really want, because you need to be able to tell this consumer exactly what quantity of each good needs to be purchased in order to maximize their utility. All right, so the thing that you're really aiming for here are Q1 and Q2, And remember that along the way, you want to use, that is a terrible lambda, you want to use lambda. I'm struggling with my lambdas today. You want to use lambda to basically to get you to the final answer. And then you just throw it away, right? You don't actually care about the values of lambda at all. Lambda is just a tool that's going to help you along the way to figuring out the thing that you really want, which are these Q1 and Q2 values. All right, so take at least 5 to 10 minutes on working on this thing algebraically. Pause the video, take 5 to 10 minutes to work on this, and then come back and I will go through how we should actually tackle this thing. All right, but you've got to struggle with this a little bit. Right, it takes a little bit of effort. So go do that right now. All right, so the idea that I had for how to solve this thing, there are many ways that you can go about solving any one of these systems, but the way that that I tried that seemed to work out fairly well was to try to make these right-hand sides of the first two equations, lambda p1 and lambda p2, agree with one another so that we can set them equal to each other. So in particular, the thing that's missing from the first equation would be multiplying through by p2. So we could multiply through on both sides by p2. And in the second equation, it would be multiplication by p1. Right, so p1 there, and we would have to multiply through by p1 on the left-hand side of the equation as well. And then the stuff on the right-hand side of the equations now agree with one another, and we could set them equal to each other. All right, so what that would end up looking like, if we do those two algebraic maneuvers and then set them equal, we would end up with something like this. We would have p2 alpha. And now I want you to notice that the exponents right there, alpha minus 1 and 1 minus alpha, these are almost identical. The only difference is that one is a multiplication of -1 of the other one, right? They're negatives of each other. And so what this means is that we could actually combine these things not as inline multiplication, but rather as a quotient. So if you think about which one of the two quantities, q1 to the alpha minus 1 or q2 to the 1 minus alpha, should be in the denominator, it should be the one with the negative exponent, right? Because negative exponents mean division in disguise. And since alpha is very specifically supposed to be between 0 and 1, that actually means that alpha minus 1 is the negative exponent. So we're going to put q2 in the numerator and q1 in the denominator. And this is really just me being, fastidious might be the right word for it. Overly careful might be another word for it. I just want to make sure that if it's in a denominator, that means that it's supposed to be in a denominator, right? It means it's supposed to have a negative exponent. So that's all I want to do there. I don't want to have, if this quotient were upside down and I did q1 over q2, then the exponent outside the parentheses would be alpha minus 1. And because alpha is between 0 and 1, alpha minus 1 would be a negative number. And so it would be like having double negatives for no good reason. So I just want to be a little bit careful about that. In the second line, copying down from the second equation, we would have p1, 1 minus alpha. And now our quotient here might be a little bit easier to see. We're going to have alpha as our exponent. And the quotient here is going to have q1 in the top, since that's the one that has a positive alpha exponent right there, and q2 downstairs because q2 has the negative alpha exponent. All right. So we've got quotients of our quantities, q2 over q1 on the left-hand side, raised to a power, 1 minus alpha, and then q1 over q2 raised to the alpha power on the right-hand side. Okay, so the idea here is now to go ahead and solve for one of the two quantities in terms of the other, and then we'll use our third equation, our budget constraint, to figure out an actual value for one of the quantities. All right, so that's how we're going to go about this. And remember, like I made a note of over on the left-hand side in that light blue color there, we want Q1 and Q2 values, and we just sort of use lambda along the way to help us get there. We don't actually care about the values of lambda. All right, so we used lambda as like a go-between, a sort of mediator that let us connect the two equations, the first two equations together. And now we're pretty much going to forget that it exists, right? It's gone from our consideration from now on. All right, so what we want to do here is solve for either Q1 or Q2. It doesn't really matter which. So, you know, whichever one you like to solve for, it doesn't really matter. What I might start off by doing is by multiplying, getting rid of the denominators, essentially. Right? So if I take this Q1 down here raised to a 1 minus alpha power, and I go ahead and multiply it over, let's see what we get. All right, so I'm just going to recopy a little bit. We're going to have P2 alpha, Q2 to the 1 minus alpha. And while I'm at it, I am also going to take, let me grab a different color here. I'm also going to take Q2 raised to the alpha, and I'm going to multiply that over, just so both my denominators are gone. All right, so I'm going to have Q2 to the alpha. And now I've multiplied over, so I'm going to have P1, 1 minus alpha, Q1 to the alpha, and now I've multiplied Q1 to the 1 minus alpha over as well. All right, so this is what our equation, which was just in orange, this is what it looks like now that I've gotten rid of the denominators. And so you can see that something nice happens here. These Q2 to the 1 minus alpha times Q2 to the alphas will cancel. Ditto for Q1 on the other side of the equation. And so what we're left with is a fairly simple, fairly elegant formula. We're going to have alpha 2 P2 Q2. I'm sorry, alpha P2 Q2 is going to be equal to 1 minus alpha P1 Q1. All right. So what this is going to give us, maybe we can solve for Q1, right? Maybe that's the quantity we're going to go ahead and solve for. So that would tell us that Q1 is going to be alpha over 1 minus alpha P2 over P1 times Q2. All right, so again, there are a ton of unknowns in this, but this is a fairly elegant looking expression, especially based on, if I just scroll back up here, right, based on the mess that we started with, to get an answer that is this, relatively clean looking is nice. Right, so it's not always expected that you get something that's relatively clean looking, and this looks, decent considering where we started. So to finish this off, what we want to do now is use the equation we haven't used at all, which is our budget constraint. All right, so we know the quantity, the relative quantities that we want to purchase, Q1 in terms of Q2. So now go ahead and plug that into our budget equation. And this said that P1, Q1, which we now have a formula for, which is alpha over 1 minus alpha, P2 over P1 times Q2 All right, so that's P1 times Q1 with Q1 replaced by that whole expression, plus P2 Q2 should add up to the consumer's wealth, their budget that they want to spend. All right, so something nice happens. The P1s cancel, and I'm left with alpha over 1 minus alpha P2 Q2 plus P2 Q2 equals W. And of course I've got P2 Q2 that can both be factored out. So what I'm left with is alpha over 1 minus alpha plus 1 P2 Q2 should be equal to W, and that's just factoring out both of those P2 Q2s. All right, so now just simplifying this fraction in here, I'm going to have alpha plus 1 minus alpha over 1 minus alpha P2 Q2 should be equal to the consumer's wealth. And upstairs in this fraction, I've got cancellation. So solving for Q2, I've got, what would I do here? I would divide by P2 and multiply by 1 minus alpha. So I've got 1 minus alpha W over P2. All right, and this value sort of makes sense if you go back to the very beginning of what we were talking about with this, right? So all the way back up here, let's see here, that's not our original utility function, so let me go back a page to here, and there's our original utility function in this green box here, our objective function. 1 minus alpha was the exponent that was put on Q2. Right, so it's like relatively how much you value Q2, product 2 compared to product 1. And now if you jump back here and you look at our quantity Q2, how much our consumer should buy of quantity of good 2, well, that exponent 1 minus alpha comes back, and so does the price of good 2, which is P2. All right, so it sort of makes sense that the amount that you should purchase of quantity 2, the quantity you should purchase of product 2, which is Q2, should only depend on how much you value Q2, or how much you value product 2, which is given by this utility exponent 1 minus alpha, and how much good 2 actually costs. All right, and then Q1. If you do the exact same thing, you should come up with a very similar answer. So I'll leave that for you guys as an exercise. Just double check that you actually do get a value for Q1 that looks sort of similar to this one. It's almost identical. And the only thing left to sort of verify to yourselves is that you've actually maximized this utility function, as opposed to the other option, which would be that you accidentally minimized it. Right? This is always a possibility. You could have accidentally minimized it, which would be a disaster. Right? That would mean that your consumer is the least satisfied with their purchase, as opposed to the most. So I'll let you guys think about why we did actually maximize it as opposed to minimizing it. But this is the gist of how a calculation like this goes. And the last thing I want to say about it is that an objective function that looks like this is a very broad class of functions in economics. These are known as Cobb-Douglas functions. And they're very, very useful, not just for utility questions, but also for figuring out how to balance things like capital, which is your money, and your labor in order to maximize production. All sorts of questions like that in economics. And they all came from these two economists named Cobb and Douglas.